So the presentation today is Turn Your Data into a Crystal Ball, how big data analytics can target energy savings opportunities, as well as predict impending system failures to achieve improved energy efficiency, comfort, and sustainability. That's a really, really long title, but today we're going to be talking about predictive analytics, big data, fault detection in buildings, really. Focus on predictive faults. Here are the learning objectives. Understand how building automation data can be used as a tool for fault detection and predictive analytics. Understand how predictive, I hear somebody on the background. I'm just going to try to, before I go on, just so we don't, could be Dan, no, looking to see who's not muted. Just make sure everybody's muted. It could be
cheapest place to go, probably on Amazon.
Michael, maybe Laura, Daryl. It might be. I hate to call people out right now. No problem. Just remember to mute your light. Okay, I think we're okay. Okay, I'm going to continue. So the third learning objective, I'll talk a little bit loud, is to identify the economic and environmental benefits of big data analytics and predictive maintenance, and finally recognize and appreciate high-value data points. This is something that I really want to talk more about in the coming year with people, potentially at events. You know, talk a lot about high-value data points, data sufficiency, what you need for analytics, and for new construction, for existing buildings. So I won't go too much into this in this presentation, but that's very important, and it's been codified in ASHRAE 36. And so data sufficiency is very important. And so if you want to talk offline again about even that more, I would love to have that conversation. So I'll start with a comparison of different maintenance programs, and then we'll arrive at predictive maintenance. The first, I'll be talking about all of these, I'll be talking about the key drivers for when the maintenance activities should be performed. And that's really the differentiator, when it's performed and when you're catching the failures. So the first is, you never want a reactive maintenance program. It happens, right? You're putting out fires, resources are limited. These repairs are completed after equipment failure, so not ideal. You're putting a Band-Aid on it, you're replacing it under unideal conditions, meaning you're usually rushed with an unplanned stop. The key driver here are actual BAS alarms, hot and cold calls from people, actual visual inspection that something has broken or a valve has started to leak or whatnot. But you're really limited to alarms and hot and cold calls, and then just failure. A coil is frozen, you know, in the winter, and that happens. And so we're trying to avoid those sort of things. The shortcomings of reactive maintenance, of course, is you're not going to have any performance improvement. You're not addressing the root cause of the issue. You're not usually addressing the inefficiency, maybe in operation. You're doing a quick fix, a quick repair to get that piece of equipment up and running as fast as possible again. So you usually, this sort of maintenance is high cost. It's unplanned. You can't take the time to properly manage your resources and to find the best options and things like that. So you're really limited, of course. Next best maintenance program is a preventative maintenance program. And these have been the backbone of historic or of mechanical industrial equipment operation for decades. So everybody's familiar with preventative maintenance. It's really designed to prevent or mitigate the consequence of equipment failure. You're replacing worn parts and worn components before they actually fail. These activities can include partial or complete overhauls at specific periods of equipment or parts, oil changes, lubrication, etc. In addition, workers can record equipment deterioration, right? And they can keep track of that. When equipment is installed in a building, designers will take note of component lifetimes, operating hours, wear parts, rated cycles, lubrication, etc. Usually run hours is the key driver for when maintenance activities should be performed. So you're not optimizing when you're performing these maintenance activities, but ideally the perfect preventative maintenance program would schedule all of this maintenance so that no failure occurs. Of course, that's not found in practice to be true, but you can help automate the preventative maintenance program through a computer maintenance management software package, a CMMS software package. This requires the user to create schedules, to have information about the equipment, design information, and things like that, and to enter that into the tool. These packages, though, they can be coupled with spare parts inventory, repair ticket tracking. Have I been muted that whole time?
Yeah, sorry, I muted all, and you please unmute yourself. Thank you.
Oh, okay.
So we can hear you now. Yeah, thanks.
Okay. So I'm going to go back. Can you still hear me, everybody?
Yes, you were only muted. This is Tara from GPAE. You were only muted for like 30 seconds.
Okay. I panicked, everybody. I thought, oh my gosh, not like we're that far in, right?
Right.
It's not like we haven't talked about any hardcore physics or anything yet. So anyway, as I was saying, and I'm unmuted again. Okay. As I was saying, you can automate a lot of the preventative maintenance, not automate it, but you can pair it with the CMMS package, and that can help you with spare parts and things like that. It can help you. There's a place now for that information to live. However, most CMMS packages don't provide analytics capability, and hence they don't allow the user to gain knowledge of the performance of their assets over time. You're not going to have a ton of data and analytics run on that to know how your equipment's been performing over 10 years potentially under different conditions, weather conditions or operational conditions, things like that. So here we're scheduling the maintenance before failure using essentially run hours is the biggest driver. I talked about some of the shortcomings, the no analytics, and you do have increased risk of failure here because deviation from normal inspection operation is limited to visual inspection a lot of times. This is a manual process. You know, you don't have a computer and some sort of software running in the background to do all this for you, of course. It requires equipment knowledge, some manual bookkeeping, but again, it's been used for decades. Predictive maintenance programs is really what I'm going to be talking about today. Here we are using data analytics to detect equipment faults and operational inefficiencies to eliminate the root cause before failure. So we're not just preventing failure, like in preventative maintenance, by being really good about maintaining our equipment. I'm getting a call. But here we are actually eliminating the root cause so that this failure won't continue to happen in the future. And that's important. Sometimes in a preventative maintenance program, you might be fixing, you might be fixing valves and things like that. Sorry, I'm getting another call. But maybe you're not addressing issues with loop tuning that are causing those valves to fail from the beginning. So that's what I mean by root cause. Really what the analytics software allows a site to do is to see the absolute root cause of something, whether it's a control sequence that's wrong or whatnot, and then eliminate that so that this failure doesn't keep on continuing to happen over time. So the key driver for predictive maintenance is automatic fault detection and diagnostics, and that's what we're going to be talking about next. This does require configuration. What I mean by that is you're going to set up your data analytics. You're going to have to, you know, either you or the company you're working with, name all that data, right? Set it up, create your model. And you're going to have a large amount of data to store, to collect, and so you just need to be prepared to deal with all that big data, and we'll talk about that. Go to the next slide. So predictive maintenance, we talked about it just now. Continuous automated analysis of equipment performance, again, to identify faults and the root cause of those faults before they become critical. We're eliminating root cause here. In this way, we can increase plant availability, increase the mean time between failures, because we're catching more faults. We're implementing them, correcting them quicker, because we have more directed suggestions. It's not just, oh, this valve, it needs to be repaired. We know why, exactly what's going wrong, and data sufficiency helps with that, with root cause analysis. So we can tell them exactly the root cause of the failure. So you're going to have fewer accidents. You're going to be able to optimize spare parts handling and things like that, because you can plan this work. You can plan it months in advance. So you can end up having a more cost-effective maintenance program that way. You're going to have cost savings over routine preventative maintenance, because this is the right information at the right time. I really like that quote. Really, what predictive maintenance is doing is you're predicting when the corrective maintenance action should be performed. So you're no longer sending people out and some equipment's replaced too early and some is too late. This is really telling you the exact time that you should be looking at something like an air filter, for example. So the key driver, as I say, or the keystone of the predictive maintenance program is the automatic fault detection and diagnostic engine, the software. That's where all the thinking goes down, and it automatically, as the name implies, detects faults in your system. So there's 4 key aspects to AFDD technology. The first is universal connectivity. This is connectivity at the point and system level, real-time and historic data, historic or legacy systems, modern BAS systems, meters, connecting to all of that, standalone controllers. You really have to be able to connect to a wide variety of systems. Secure big data collection and storage. That involves not only pulling in massive amounts of data and storing it. Again, that kind of goes back to that historic asset performance over time, right? You have to be able to store data for an entire site over years and years and years. So not only pulling it in and storing it, but also working with the IT department and their tools, and increasingly stringent security requirements. Recently, those were codified in BACnet SC. Digital security certificates and handshaking and things like that. We could talk an entire day about that. And I'm also very passionate about that, because that's going to be extremely important. But we won't talk about security today. But collecting data, storing it, and doing that in a secure way. Topological system modeling. This refers to the mapping of the relationship between all of the pieces of equipment that make up the HVAC system. So how the plant, air distribution equipment, and zone or terminal equipment, how that's all connected. That's very important to avoid the problem, and I'll talk about this, I think, in the next slide, to avoid the problem of islands of automation. In order to find root causes, right, accurately, and to get at the real problem, we need to see the interconnectivity of all of the equipment. A fault downstream might be caused by something upstream. There could be the fault of a ubiquitous small piece of zone equipment that can be causing a problem. So we need to look at everything. And I'll talk about that scalability that I kind of mentioned. The fourth aspect here is the automatic fault detection and root cause analysis itself. This is the AFDD software, or the engine, or the platform that in some cases runs thousands of algorithms on the BAS data. It finds inefficiencies and failures. A human could do this in like the entire course of their lifetime, because not in real time, because we're talking about sometimes millions of data points, and as you know, sometimes hundreds of pieces of air handlers and things like that. This AFDD system, which is what I'll call it, AFDD, this was going to find failures from simple mechanical failures like a valve leaking by or passing, when intended to be closed, all the way up to suboptimal sequences of operations like economizer mode, you know, enthalpy, temperature-based, dew point-based, and other things like issue recurrence, scheduling, you name it. Depends on the points, right? Depends on what we can see. So PDM, which is predictive maintenance, I might call it PDM, we're really utilizing the AFDD here and the data. So I'll talk a little bit about big data, buzzword. Oh, by the way, talking about buzzwords, the topological system modeling, you might hear the term digital twin. I hear that a lot. That's essentially the model of the building. And that's what we're developing here by getting all of this data, naming it correctly, you know, having the right topology, and then all of these algorithms are running on that model, the model of the building. It's a digital model, right? How it's running. But you might hear that word, digital twin. So with modern big data approaches, we can increase the effectiveness of PDM. We can get data, have data sets from sensors all around the process or the equipment to really build a composite view of systems operation, not just this is what this air handler is doing or this is what this chilled water pump is doing, right? We need to look at the entire system. By doing that, we can correlate, for example, maintenance data to building comfort or the integrity of a manufacturing process, you know, more complex analysis now that we can see how all of those pieces of equipment and spaces, physical spaces in the building, zone temperature sensors and knock sensors, things like that, how it's all connected. In the past, predictive maintenance was more limited to high value assets. You couldn't really mine your system for data for value and look at every low cost, you know, or low value asset. So what's different today is we can automatically collect and analyze enough data. I think, what is the storage? I've read that every couple of years, essentially, the storage capabilities double, right? So we just have access to a ton of data that's stored. So now we can apply predictive maintenance to even small endpoint devices, such as VAV boxes, for example, process utility connection points. You really can scale AFDD down to detect even minor anomalies and failure patterns. This allows you to determine the assets and operational processes that are the greatest risk of failure. Sometimes not always the highest savings, you know, but important for other reasons. Is this a lab space? Is this a manufacturing space? So really important, this piece, the modeling, the topological modeling, and the fact that we can scale down and scale up, of course, to multi-building sites. So I won't go through every single one of these examples because we're about to show you some examples. But predictive maintenance can include observation of equipment performance drift, for example, vibration analysis, critical parameter process monitoring, monitoring equipment during severe weather conditions, and predicting periods of time where that might be an issue. That's very important, especially when you consider the possibility of frozen coils and people being uncomfortable during severe weather as outside of ASHRAE conditions. And we'll talk about that in an example. We won't discuss every single one of these. Really, it depends on what data we have, right? We can only look at bearing temperature if we've got that point, and some points are more rare than others. I am excited in the future, you know, of data, right? We'll only get more data, and with Haystack and all these other things, I think we can look forward to more data in the future always, right? So I'll go into my examples now. This is the first example. I'll first show kind of a plot, and then we'll talk on the next slide about some summary points like the symptom, the root cause, what was predicted, the solution, and then the savings. That's what I'm going to talk about for each one of these examples to try to keep us organized, because we can get fatigued with these examples. I know people have seen a lot of time series charts sometimes and heat maps and things like that in data presentations. So I'm aware that this can get dry, but I think these are great examples. So predicting valve failure, I will mention the majority of these examples are from local customers from the Pennsylvania area, Philadelphia area, in pharmaceutical, research, healthcare, higher ed, and commercial. And I'm keeping the names redacted for today, but it's sometimes you look at these examples and sometimes, oh, look at all this failure, and you might say, oh, that's a bad thing, but I'll try to highlight the situations where, wow, I mean, this was really fixed within 30 days, and that's pretty amazing. So, and also sometimes showing when real life happens, right, and the valve will go on oscillating for a year. That's just what happens. So anyway, those are the customers I'll be using as examples, and all from your area, most from your area. So this is from a pharmaceutical company. This is a valve failure. Now, how do we predict a valve failure? We can look at the oscillation of the valve, right? You can also look at set points and say, you know, there's set point disagreement, and that can cause some of this too, and I'll show you how in a second. Now, this is a time series chart, so we have time on the bottom. That's what most of the charts shown today will look like. So we have March, May, December of 2017 here, and it goes on. And then this is our y-axis with temperature and valve signal. The gray here that's oscillating, that's the preheat valve signal, and the blue in the bottom, I'll use my mouse over here, that's the chilled water valve signal. The discharge air temperature is shown in green, and the discharge air temperature set point is shown in black. Now, this valve was oscillating for a year before this valve failure. We have a metric, we call it rate of travel, but it's essentially says this is how much this valve is oscillating in a minute or in a certain period of time, right? And anything over this number, it's going to lead to equipment degradation. We have, you know, 30 years experience to know what that number is and what's bad. There's also rated cycles for equipment, but we can really fine tune this and be able to help the team loop tune. You know, this is a situation where they might want to tune the loop. So you can see this oscillation. You can see in the preheat discharge air temperature, which is yellow, it gets up to 90 degrees. It's oscillating between 90 degrees and 50 degrees back and forth. These valves are oscillating, and without analytics, you might not know it at all. You might not have any indication, because generally you're meeting your discharge air temperature set point. You can see here in January, the valve completely fails, and the preheat discharge air temperature increases well above outdoor air temperature, even though the preheat valve is signaled closed. That's an indication of a passing valve, I should say. So we can see a huge preheat discharge. The savings on this are huge, and here's the reason. We're heating 30 degrees, and then we're cooling 30 degrees to get back down to temperature. And an old colleague of mine used to call these insidious faults, and I really like that term because it would go undetected. You wouldn't get a hot or cold call. You would never know that this was happening. You'd still meet your temperature, and you would be wasting a ton of energy, and it is not how the system is intended to run. They replaced that valve, and we're working on the loop tuning. So here the symptom was signal oscillation. Sometimes we can actually see, like I mentioned before, a set point, a disagreement. So a preheat set point and a final discharge air temperature set point might be so close together without any deadband that you're constantly oscillating the valves to try to meet those two set points together. So we can predict sometimes oscillation before that even occurs by looking at set points and saying, in winter time, you're going to have a problem. But usually we look at oscillation. The root cause here is a poorly tuned temperature control loop. Sometimes it can be set points, as I mentioned. The prediction, what we're predicting is the valve failure. We're predicting that valve's going to fail, and we're going to blow steam, and simultaneous heating and cooling is going to occur, and you could potentially have comfort issues. The solution here is to tune the control loop. That's really eliminating the root cause. In a preventative maintenance program or any other maintenance program, if this happened, you might repair the valve and move on, right? Oh, the valve's blew, let's put in a new one. It's gonna, maybe if the tuning hasn't been addressed, you're still gonna have that oscillation, and you're gonna have failure in another few years or potentially sooner. So root cause is very important. And here the savings were $173,000 a year. What are these numbers? This is an annualized number. I always get this question. So if that fault that we just saw had happened for an entire year, without being repaired. That's what that number represents. We have methodology and assumptions and all of these things, but generally, the more airflow that the unit is providing, right, more CFM, the more hours it's running, so operation, 24/7 operation, the more savings you're going to have, right? And your delta T. You're really looking at your delta T, your delta temperature, your delta airflow, and how many hours you got. And that's, for this case, your savings. By the way, the loop tuning, I won't go into it too much, but that's not necessarily straightforward, especially if there's issues with nonlinearity and things like that. So sometimes loop tuning can take 6 months, a year to get somebody in and really tune the loops properly. So it's not trivial. The next example is compressor cycling. I'll shoot through this pretty quickly because I think we're familiar with this sort of thing. Short cycling of equipment. I used to do audits, and I remember hearing pneumatic systems, the compressors in the basement cycle on and off, and that meant there was a leak in the pneumatic somewhere. We'd go around listening for hissing like through the walls. But this is short cycling of a compressor for a chiller. And here we saw cycling. It also shouldn't have been running at this time. Anyway, the chillers were cycling on and off because of the differential pressure set point. There was no dead band there, and it was hunting. And that was for freeze protection. These units never should have been on, actually, and these were turned off shortly after. So the symptom here was short cycling. The root cause was the pressure controller DP was set too tight. Other causes can be charge, refrigerant charge, and things like that. The prediction was a reduced equipment lifetime. We didn't take savings here, but you absolutely can take avoided savings, for replacing that potential piece of equipment. And here the solution is to increase that DP dead band to give it a little bit of room, but really the chillers were not supposed to be on. They were left in hand in this situation. This was serving a vivarium, I think. Fouled coils, this is the next example. Let me go up, sorry, sorry, okay. Fouled coils. Here, the savings are pretty big for this one. This is somewhat surprising. Here we have a situation where the duct pressures are below set point. And that's what the fault engine is reading. Okay, we're not meeting set point. In this case, why? That was the question, and we could deduce that it was fouled coils. So after the coil replacement, all the duct pressures were maintained at their set point, and we were delivering more air at slower speeds using less fan power. The problem here when you have fouled coils, besides energy waste, is it's really not good for equipment. It'll degrade the equipment, right? You're going to be running your fans at higher speeds. I'll go to the next slide. You can blow your fan motor. You have decreased heat transfer, all that stuff. You're trying to work harder to push air through the piece of equipment. Indoor air quality is a problem. I used to kind of gloss over that in all these presentations. It's funny now, right? That's huge. Indoor air quality, fouled coils, and what can get stuck to those coils, and how are you going to get that stuff off those coils often enough? And so analytics can really help you look at that. Symptom, discharge air pressure below set point. Not just below set point, we can see how much below, how long has it been below set point? What was it doing 2 years ago? Was it this below set point? We really can get better information to the customer to help reduce that implementation period and make sure that that issue is solved quickly. The root cause here were fouled coils. Equipment failure, I talked about some of what we're predicting, what could possibly happen there, the consequences. An easy, well, I say easy, straightforward solution to clean them. You can do this power wash, or I've heard of UVC and things like that. There's a variety of ways to clean coils. That's not my expertise. Savings was $113,000 a year for fouled coils. And that's not thinking of the indoor air quality issues. I'm always shocked as a mechanical engineer, it makes sense, right? A dirty coil, you're not going to get as much heat transfer, but wow. Here's a dirty air filter example. This is one of my favorite examples that I've spent a lot of time with. Dirty air filters, I think, are a great example to talk about the differences between preventative maintenance and predictive maintenance. This, first to show the plot, it's another time series chart. In orange is our differential pressure alarm. This is an actual alarm point from the BAS. The blue is the differential pressure across the air filter. And I'll talk about this yellow, but this is essentially the accumulated cost of not replacing that fan. So in a preventative maintenance program or a reactive maintenance program, you might see this alarm come on, this differential pressure alarm come on, and say, oh my gosh, I need to replace my fan. You'll see it's sporadic in the beginning because their differential pressure is kind of jumping above some sort of set point that alarm is set for and then dropping below. So your alarm is kind of flagging on and off. I'll mention that persistent alarms or alarms that do that are oftentimes ignored because they're not trusted, and other alarm points might not be working right, and so you might assume that all are bad. So that's another problem with just relying on an alarm point, and that's a big way that analytics can help you. It actually can find sensor errors, and that's a big part of what we do. But so you might replace this fan right away. Oh my gosh, it's an alarm now. It's been an alarm constant now in April. Or you might say in a preventative maintenance program, you know what, I have this thing scheduled for a fan replacement in 2 months, along with these other 5 air filters. I'm going to wait, right? A preventative maintenance program would likely result in replacing that air filter. I always say fan filter. Replacing that air filter either too soon or too late, inevitably. What does too soon mean? What are the consequences of too soon? You're not going to have a fan failure or a filter failure, but you're going to waste money. And when you think of how many filters are in buildings, some air handlers have 4 different filters. You can have thousands and thousands of filters. This is a significant cost. I'll show you how it can add up later. But so in a predictive maintenance program, it's entirely different. You're going to predict the optimal point to change that air filter. The optimal point is going to be a time that minimizes, right, your total cost. So there's a cost to running your fan at increased pressure. You know, you're having to overcome that differential pressure. Your fans are going to work harder. But that's what this yellow line represents. And I've seen presentations where people talk about this air filter optimization, but you're waiting until the cost of that dirty air filter reaches a point that you've determined to be optimal. And then you're going to say, replace your fan here. So you can see in this chart, the customer, the AVP increases. You see them repair it right here. After repair, we see, oh, you can't see my mouse. After repair, we see this differential pressure in blue go back down to set point. It's at about 0.2 inches, water column. Now, quick highlight, how cool is it that we can help verify that work was performed? Sometimes we can show when the equipment was down and work was being done. And I never use the word watchdog because it's always a partnership. Increase in DP is the dirty air filter symptom. The root cause was the dirty air filter. I talked about this a little bit. Your prediction, you can have frozen coils from this because you don't have enough airflow. You can have blower failure, inadequate heating, cooling, etc. So we optimize the time period between air filter replacements. Savings is only, I say only, $900 a year for this filter, but that's for one filter. Think about 2,000 filters in your building, and also think about what we're not talking about, which is just a more streamlined maintenance program. You know, you're going to save not just in energy, but in people's time. There's plenty to do on a site, plenty other things they can do on a site. I'm going to go quickly through this example. This is a weather alert. We just see some alarms here flagging that are going into alarm mode when the OAT drops below freezing. Really, I just wanted to use this as an example of when we can flag air handlers that are susceptible to frozen coils for an upcoming cold spell or hot spell, for example. When we're towards ASHRAE design conditions for weather, that's when we're going to monitor this equipment and predict units that will have problems, again, based off of past operation and things like that. In this case, we actually were asked to show this whole issue so that they could get money from the contractor. I say usually it's an entire partnership and we're not really a watchdog. In this case, we found low stream temperatures. There were 100% outdoor air units. There was inadequate freeze control logic. I won't go into all the freeze control logic now, but certain air handlers were flagged. They were susceptible to frozen coils. Sure enough, they froze. We suggested freeze protection control sequences and things like that. And the contractor admitted negligence here, and they were responsible for $60,000 of damages from frozen coils. The coils froze here. And that really, you can imagine the cost of that. Excess runtime, this is a scheduling issue. We can see, we use these charts of bubbles. You can see that this size means 24/7 operation. A lot of times we'll see something scheduled, go off schedule. Scheduled, go off schedule. We can help kind of understand, why is this happening? Why is this unit not staying on schedule? Sometimes it's a change of space, a use. And we can help identify that. And we actually have. We said, you know, does this need to run 24/7? Maybe it can be placed on a schedule, or maybe it was on a schedule and we're finding it can't be anymore. A lot of times equipment is left in 24/7 operation because of an unknown in response time. I found that people don't know, how long is it going to take for my space to get up to temperature, right? I don't want to have some unoccupied set point and let it drift, and now I'm getting hot and cold calls in the morning. I'm just going to let it run 24/7. That was the case with this unit. There was steam piping in the ceiling. They were really nervous. Even though it was insulated, it was getting really warm in a room. And another customer, local customer, they had a gym that was operating 24/7. And the contractors and the team worked so hard to prove that we might not need that unit to run 24/7. I did a savings calculation to show them how much they would save. I think they installed occupancy sensors to actually prove that people weren't using the gym 24/7. So givens that in the past have been, oh yeah, that needs to run 24/7, kind of we can help facilitate a conversation about, does it, you know, has something changed? You want to test it? You want to test this time and let it run a few days, look at the response time. Here we actually had to install a software switch with a maximum runtime because of the change of space requirements. Anyway, long story short, that's about a $50,000 a year issue. I've been supporting people too recently with COVID shutdowns. If you want to talk offline about that, I would love to. But a lot of people are working hard right now to shut down equipment and make sure buildings are operating right now. And anyway, I'm very humbled by all the work that people are doing. So I'm trying to support people. Here, this example is response time. This is what I was talking about before. Why air handlers sometimes are operating 24/7. This is kind of more of an AFDD example, maybe not necessarily as predictive. But here you can see an unoccupied cooling set point of 82 and an unoccupied heating set point of 61. You can see that huge deadband between those set points. Now, what we're trying to find is the response time of the space. How long does it take for the space to get to temperature in the morning to make it to set point? The answer is this room couldn't possibly get to temperature in time. You can see it cannot respond in time in the 10 hours or so that it's occupied. So we can help give customers that information that the symptom here is that zone temperature set point wasn't being maintained. And people might say, gosh, why is that? They might change the occupied set points a bunch of times and try to figure that out, and without seeing that response time and fine-tuning the deadband. So here we had to fine-tune the deadband. But knowing the response time is powerful because you can better schedule equipment by having that information. And that's some of the asset performance over time that I'm talking about. You know, understanding how all this is related and how zones, how long it takes for them to get up to temperature, right? That's all dependent on the space volume, the people in the space. Pretty complex problem that we can help solve. I just have two examples left. Operational mismatches. This is a seemingly simple one, but I think it's actually really powerful. So this is referring to supply and return fan disagreement. For example, in this plot, we have our supply fan speed is 100%, our return fan speed is 0. Or in this case, we have a command status mismatch with a boiler. So we find this so often that equipment is left in hand, and this can lead to overridden control strategies and just a lot of unintended gonna make sure I'm not muted. Unintended consequences. You might think your equipment's running a certain way because you're looking at a point and it's actually not. Again, analytics, how else are you going to determine that when, for example, this site, this is a university campus, the site has an average of 45 pieces of equipment in hand per month. That's pretty typical of a big site. Again, you need some sort of analytics to help you parse through this and determine also what are the highest priority units, because you're going to have to put all these on a list and go take them out from being in hand. A lot of times, too, there's savings here. You could be commanding your unit off, but it could be running, and it shouldn't be. So there's significant savings there. Basically a scheduling calculation. So operational mismatch. Here we're talking about points that disagree. Sometimes the point itself might be bad, and we can help determine that too. This BAS point is out to lunch, and we need to repair it or replace it, the sensor point. Equipment operating in hand, that's the root cause here. Or the supply and return fan aren't properly interlocked, the controls. They should be interlocked so that you don't have pressurization issues. Again, I kind of used to breeze past this, but how important is this in our post-COVID world, that those fans are interlocked, supply and exhaust fans, supply and return fans, that you don't have negative pressure, and that can be dangerous for air quality, as we all know. The prediction here is that the control sequences were overridden. And here, you can release the points as the solution, make sure those fans are interlocked. Also check to see that fan motion is not restricted. If your speed is less than your signal implies, then there might be a restriction there. And again, that really does lead to equipment degradation if it's restricted in some way. It's not operating how it should be. You could have increased heat and things like that. Last example, I swear, is excess heat recovery. This is more of an analytics example, but I wanted to include kind of a complex sequence of operations example. Here's the time series chart here, just the 2 points that are important. Most important, this red dotted line is the energy wheel signal, and this orange line here, I need to point to it over here, is the energy wheel discharge temperature. What did we find? We found that the energy wheel was running 24/7, 100% speed, and we were recovering excess heat from the exhaust stream. So we need to modulate that energy wheel. We need to control that temperature to an optimum value. And so what we found was that the control logic was inefficient and inconsistent with the control package sequence of operations. And I put that here in the slide, a little piece of the control package. We talk a lot about data and we give the AFDD engine so much credit, but there is an analyst to provide a lens through which these findings are interpreted. And I work with real people, and I read real controls documents, and I help parse through kind of that manual stuff that one would have to do in a preventative maintenance program. But we take all this into account, and that's kind of what we mean where we monitor equipment performance as compared to optimal design. This is a perfect example. Economizer is another one that I find a lot. Inefficient economizer control, it's not based on enthalpy, or it's not as intended in the control sequence. Again, things can drift over time. This control sequence is what, 40 years old, or but in this case, I want to mention this was a new building. So this issue was found within the first year of operation. Why do we care about that? This was still under warranty, which is great because you can actually go to the controls installer and say, there's an issue with the sequence here. And so in that way, I'm showing a way that analytics is used for continuous commissioning. I hope everybody can hear me. It can be used for continuous commissioning and onboarding commissioning for a new building. And before you think, oh, it's a new building, I'm not going to find much. We find, I wish my colleague were here, who has worked with a lot of new buildings. He could tell you just how many faults he finds in brand new buildings, how we can support people to get it fixed under warranty. If you don't do this, you can have unintended energy use. Your whole system is set up for this heat recovery. So you can have chilled water valves that are starved. You can see, 10 degrees above set point is what we're overheating here. Anyway, you see here, the valve was shut down for repair, and it modulates here. We're still seeing excess heat, and And here we're starting to get into cool recovery mode. So this is one of the more complex issues that we find in terms of control sequences, but pretty straightforward still. 11 air handlers had identical problems like this. 11 air handlers. So a whole bank, if you want to call it that, of air handlers didn't have their heat recovery working. That's significant. Imagine if you don't find that for 2 years and now nobody knows whose fault it is or the root cause. And it's not about the fault, but it's about repairing it under that warranty, identifying it then. So the symptom here, high heat wheel DAT and 24/7 operation. This was inconsistent with the sequence of operations, which showed different periods that it should be modulating and shutting down, et cetera. This can lead to equipment degradation. It's running when it shouldn't be all the time, flat out. So you could actually have equipment failure sooner than intended, sooner than all of these design documents estimate, right? You can have a starved chill water valve because you're introducing so much excess heat that your system wasn't rated to handle that, to cool that back down to set point. You can have comfort issues, therefore. So here you want to correct the control sequence, make sure that wheel is modulating. If it has a VFD, you can install one on it if it doesn't. And in that way, we can help justify capital projects. We do that a lot where you can justify installation of a heat recovery coil, or you can justify the installation of additional sensors and BAS points by saying, if you do that, we can save, you know, $30,000 a year, for example, on heat recovery. In this case, it was $3,000 a year for that one air handler, and for all 11 air handlers, it was $45,000 a year. And again, that doesn't take into account the other consequences. I'm just going to finish up data sufficiency. This is what I mentioned in the beginning of the presentation. I would refer you to ASHRAE Guideline 36, but I'm really looking forward next year to talking more about data sufficiency in onboarding in new buildings, even existing buildings, really talking about what points do you need to have a strong analytics, capabilities. So also, how well does AFDD data condition? This is a really important question. Point naming, point topology, and data conditioning. It's a lot of work, and it's critical for your engine to work properly. You don't want false flags, right? You want these faults to be real, and it's dependent on your data quality and and the analytics capability to data condition. So interpolation, cleansing, sensor errors, things like that. Your fault detection, your predictions, your pointed suggestions for your root cause and for implementation, that's all dependent on data quality. So lastly, I guess I would just say that this root cause analysis really helps streamline issue remediation with people. It helps them on the field. They have to go fix this stuff. You know, you can't just say, oh, we've got a high discharge air temperature. We don't know why. You know, it really helps to dig down. So I like to stress the importance of the role of the analyst, me, to keep my job, right? To provide a lens through which these findings are interpreted, and also to be a partner to the team. There's a lot of problems on these sites and not a lot of resources a lot of times, and so I'm there to help. I'm there to interpret, like I said, these findings and help parse through all that. So anyway, in that way, I owe it to all of the examples, the customers above, because it's been excellent to work with them to help fix these things. So, questions? Oh my gosh, 10:58. I'm going to go ahead and pull up my participants list here.
So if you would like to ask Julianne questions, please raise your hand or unmute yourself and ask question.
So there were a couple of questions in the chat near the end of the presentation. There was a little bit of a discussion on COVID. And that can be, sorry, this is Hadassah. I lead the analytics team at Cimetrics. We could have a whole other conversation about COVID. But while Julianne catches up, I just wanted to say that, Sufern, yes, there are going to be costs associated with the new operation in relation to COVID. You probably are going to have to run your returner systems at 100%. you may very well have to add additional equipment, UVC or different filters. ASHRAE and the CDC have been the references that we've been turning to for their recommendations. ASHRAE has been updating their standards regularly, and Cimetrics is working on developing a 2-page boiled down summary of what those current recommendations are from ASHRAE and the CDC, as well as how Analytica can be used. You asked what opportunities are available in the age of the pandemic. Most of the opportunities that Julianne mentioned in this presentation will still be there. You're still going to have oscillating valves. You're still going to have simultaneous heating and cooling. But yes, you are going to have to factor in the cost of additional outside air. We can calculate that. We had one customer come to us and say, how much is it going to cost us to run all our return air systems at 100% for a year? We gave them the estimate so they know how much it's, what they're looking at for budgeting and planning. So that was a quick rundown of what we're looking at for COVID. There's also considerations as you reopen to make sure that the spaces are prepared for handling increased capacity, and also keep in mind that Legionnaire is something you may want to consider if there's any stagnant water around. Very quick, there's a whole lot that we could say about that, but I hope that answered some of your questions, Sue Fern and Chad.
Yes, thank you.
Hey, this is
Yeah,
Mike.
thank you.
Can I ask a quick question? Hello?
Sure,
Yes, please.
please do. Yeah.
Yeah, it's Mike Castle with GSA. Only question I have, we had a real problem getting in. My whole team couldn't get in except for Rick and one other person, but it had to do with the change at the last minute. So forgive us for that, but we'd like to go. If you have more of these, we'd like to participate. But the question that I have is the 2-day, the boil down that you referred to, is that something that you can share with us?
Absolutely, yeah.
So Julian, you'll make sure we see that? All right.
Yes, Mike, thank you. I'll send that to you, and I apologize. Mike, I'll send you the recording of the presentation also, and thank you for calling in. I love to have some familiar faces here of some customers on. Yes, we recorded the entire thing, and actually, you know, some of my customers that are on today have been doing a lot of work for COVID. For example, I work with some of the contractors, and they'll do walkthroughs in the morning and make sure that certain areas are not occupied before we shut them down. We'll then shut them down. I'll verify it. So anyway, again, a really great work. Somebody is on site, you know, wearing a mask, doing all that, and I can help with the data. But it's, yeah, good question, Sue Fern and Hadass. We will send out that list. The kind of 2-pager, because I don't know if people have gone on the ASHRAE site, but it can be a lot to go through. There's 4 different tabs for healthcare, universities, you know, and the information's in different places. And it's really important information, like we were talking about, your heat recovery, how much outside air you're bringing in. So anyway, maybe we can distribute that to everybody who is on this. But yeah, thank you for that.
And I was gonna bring up one thing too, that I'd like to kick that up since we didn't attend this meeting. I'll look at what you send me, and I'll have that with our team. But I was thinking about kicking this up a little bit to another senior level to see if they want to do that this type of presentation within our region, and see if they'd be on board with that. Okay.
Yeah, please, Mike. Of course, and that goes to anybody here. Yeah, you know, this all happened so fast, but I would like to talk to more of you who are interested in what we've done for COVID. Actually, there's a great blog article. I'm biased, but it was written by my colleague, Hadass Webb, my boss. It shows some of the work we've been doing for COVID shutdowns, and in terms of reducing airflow in some spaces. And anyway, would love to have a conversation about that too offline, and talk to people about what they're doing. I've been getting a lot of emails from customers on their different COVID plans, so it might be good to
I want to make sure I'd like to make sure that all questions get answered. Might be some questions unrelated to COVID as well. Ariel asks, which platform are you using to collect data from the building and send them back to the cloud? Are you developing your own software or using existing platform like PdM? Do you want to address that?
Thank you. Yes, thank you. So we pull, we call it a cache puller, but we collect data, you know, Cimetrics, Analytica. We attach a box to the system. We pull data ourselves, and it goes into our own cloud storage and things like that. So yeah, that's why I mentioned some of the IT requirements and working with IT. We have a lot of experience with their tools and requirements. So that's where we start the conversation. I also have an FAQ for the IT department, a list of things for the IT department if you're thinking about something like this. So if anybody's interested in that, I can send it along. But yeah, we collect our own data through our own box that we built. Does that answer your question?
She follows up and says, so are you independent of the BMS and using your own IoT?
Yes, we are independent of the BMS, yes. So we can connect to any building automation system, you know, Siemens, Johnson, legacy systems. I didn't mention all of them, and I can also give you an email with more information, but basically anything you can think of, even controllers and things on site, meters, we've had experience connecting to over the decades, over the years. So we can connect to any of those.
As well.
Yes. Trying to keep up on my messages. Also, I would mention that more and more, I'm just going to say it quickly because we don't have much time, but a lot of states are further developing their incentive programs for continuous commissioning, and there's more data to show that it is proven to work and things like that. So I would encourage all of you to reach out if you want more questions, or if you have more questions about the incentives regarding all this stuff. Not only continuous commissioning, but finding prescriptive incentives too, just using your AFDD data and the baselines that you have.
Guys, this is Tara from GPAE. I don't necessarily have a question, but I just wanted to thank everybody. I think this was a great webinar, excellent information, very useful. I'm just really glad that we can make this happen for our members today. So I really appreciate you guys stepping up and doing this for us.
Thank you, Tara.
Thank you, Tara. Yes, thank you for hosting. I really appreciate it. I love to have all these conversations. So if anybody, please reach out and call me or email me if you want to talk more. And I really appreciate everybody's time.